Hi everyone, welcome to my channel. In the series of lectures related to switching theory and logic design, we have completed the introduction of various number systems, especially decimal number system, decimal number system. Then we have covered binary number system. Later, we have seen what is meant by a octal number system as well as hexadecimal number system. Okay, so we have seen what are the characters in all these number systems and how can we convert a number which is represented in binary number system to decimal number system, and how to convert a number which is represented in octal number system to an equivalent number in decimal number system, as well as how to convert a hexadecimal number into a decimal number. We have seen all these things in our previous 4 or 5 classes related to number systems. Now, in this class, we will see the reverse conversion. The reverse conversion means how to convert a decimal number into a binary number, how to convert a decimal number into an octal number, and how to convert a decimal number into hexadecimal number. Let us see one by one in step by step. So in this conversion process means when we are converting decimal to binary, decimal to octal, decimal to hexadecimal, we follow the same procedure. We follow the same procedure. That's why if you understand one conversion, you can do the remaining all conversions. But first conversion must be understood very uh, properly. Then only you can go for the remaining conversions easily. Okay, let us see the first conversion, which is decimal to binary conversion. Okay, so we'll follow the same procedure for each and every conversion. That's why it is very important to understand the basics. Okay, so the topic for today's discussion is decimal to binary conversion. Okay, so here there are two things. One is, if the given decimal number, one type of problem is if the given decimal number contains only integral part. If the given decimal number contains only integral part. This is one type of problem. And the second type of problem is if the given number integral part, contains both integral part as well as fractional part, as well as fractional part. Okay, so we can understand the conversion of these two models of problems with the help of some numericals, because I don't want to explain the procedure because it will take more amount of time, and if the length of this video is very high, then automatically you will lose interest on what you are learning. That's why I want to express this conversion by considering simple numericals. Okay, with the simple numerical problems you can understand the procedure actually. Okay, now let us consider the first example of conversion from decimal to binary. Okay, so I want to uh, convert the decimal number 143. Okay, so this is a 3-digit decimal number. I want to convert it into a binary number. Okay, how can I do it? So for the integral part, we will follow successive division method for integral part. in order to convert decimal to any other conversions like binary, hexadecimal, octal, we will follow successive division method. Okay, so what is meant by successive division method? You can understand just within 30 seconds. You can understand what is meant by successive division method. So first we'll consider the number which we need to convert into a binary number. So this is the number we want to convert into. So this is the number which I want to convert into binary number. Now, what is the base of the number? What is the base of number to which we need to convert? So I need to convert this number into another number which has base of 2. So I need to divide this 143 with the 2. Okay. After dividing 143 with 2, you need to write a quotient and remainder with a hyphen by separating them with a hyphen. So if you want to divide 143 with the 2, so 2 sevens 14 and 2 ones 2. What is the remainder? 1. So this is the quotient and this is the remainder, and you need to go further. Hence it is called as successive division. We are not stopping at one division. We are dividing until the remainder of that particular division is 0, or if there is no possibility of divide further. In these two cases, up to these two cases, we will continue our division. Now again divide 71 with 2. So if you divide 71 with 2, it is 235s. 2 times 35 is 70 and the remainder is 1. So I can write 1. Similarly, and again I want to divide 35 with 2. So 2 times 17 is 34, remainder is 1. Next 2. So 2 times 8 is 16 and the remainder is 1. Next 2 times 4 is 8. What is the remainder now? Now the remainder is 0. Next 2 times 2 is 0. Okay, 2 times 2 is 4 and the remainder is 0. Next last one, 2 times 1 is 2 and the remainder is 0. And you cannot go further. Is it right or not? And in order to write the equivalent binary number, you need to move in reverse direction. Okay, starting from last quotient to the first remainder. This is the last quotient. Is it right or not? And this is the first remainder. So starting from last quotient to first remainder, you need to move in this direction to write the equivalent binary value. Hence, what is the equivalent binary for the decimal number 143? So first is 1, first digit which is MSB is 1, and after 1, how many zeros are there? 1, 2, 3. So 1, 2, 3. Next, after 3 zeros, how many ones are there? 1, 2, 3, 4. So 1, 2, 3, 4. Okay. So this is the equivalent binary number for the given decimal number. Okay. So in the number system, the advantage is you can recheck your answer. You can verify your answer, because in the examination, rather than speed of your calculations, it is very important to have the accuracy. Okay, so to write a correct answer is very important rather than the speed in academic examinations. That's why we need to check, or we need to verify whether the answer we have obtained is correct or not. How can you verify it? Already we have covered how to convert this binary number into a decimal number. Is it right or not? So using that technique, convert this binary number to a decimal number. If that decimal number is equal to 143, then your answer is correct. Okay. So let me do it for your sake. This verification actually is not needed in your examination, but for your better understanding and for the accuracy of your result, you need to verify it. Now, for this one, what is the polynomial of 2? We will get 2 power 0. For this one, 2 power 1. Next, for this one, 2 square. And for this one, 2 cube. Next, as you have 0, multiplying 0 with anything gives you 0. So here you will get 2 power 4, 2 power 5, 2 power 6, and it is 2 power 7. So I am considering only the coefficients which has ones. I am neglecting the coefficients which are 0, because multiplying 0 with anything gives you 0. So 2 power 0 into 1 is 1, plus 2 power 1 into 1 is 2, plus 2 square into 1 is 4, plus 2 cube into 1, 8, plus what is 2 power 7, 2 power 7, 2 power 5 is 32, 2 power 32 into 4, 128. Okay, 2 power 7 is 128. Now adding all this, you will get 143. Adding all this, you will get 143. Okay, so this is the number which is given as the question. In this way you can verify your answer. So this entire part comes under verification. This entire part comes under verification. This is not needed to write in your examination, but for your understanding you need to write. This one is important. Okay, and this comes under first model. Is it right or not? This comes under first model because it has only integral part. Let us see one more question which comes under first model. Example 2. Example 2. And it is 44. So this is a decimal number 44, and it comes under first model because it contains only integral part. You need to convert this into binary. So binary has base 2, hence I am writing 2, and I need to find this number. How can you do it? Make it fast. So first you need to consider the number given in the problem, and you need to divide that with the base which you need to convert. I want to convert a number which is represented in decimal number system into a binary number. Hence the base to which I need to convert is 2. So I need to divide with 2. So 244. What is the quotient? 22 is the quotient. 0 is the remainder. Next, 211. 11 is the quotient. 0 is the remainder. And 2 5s 10. 2 times 5 is 10. Remainder is 1. Next, 2 times 2 is 4. Remainder is 1. Next, 2 times 1 is 2, and the remainder is 0. And in order to write the equivalent binary number, in which direction you need to move? Starting from last coefficient to, sorry, last quotient. Starting from last quotient to the first remainder. You need to move in reverse direction. Okay. Now it is equivalent to, so it is equivalent to 1 0 followed by 2 ones followed by 2 zeros. Okay, how can you verify your answer? How can you verify your answer? Just write 1 0 1 1 0 0. Now for this the polynomial is 2 power 0. For this 2 power 1. For this 2 square. For this 2 cube. And for this 0 2 power 4. And for this 1 2 power 5. 0 1 2 3 4 5. Now add the coefficients which has only ones, means multiplying the coefficients with that polynomial, you need to add all these things. I'm not considering zero terms, so neglecting zero terms, adding the terms which contains only ones. So 2 square into 1 is 4 plus 2 cube into 1 is 8 plus 2 power 5 into 1 32. 32 8 plus 8 is 40. 40 plus 4 is 44. Okay, this is the number given in the problem. In this way you can convert any decimal number into its equivalent binary number. Now let us see the second model of problems. So in the second model you must have the integral part plus fractional part. So the third example will have integral part plus fractional part. Okay, so this is related to second model. A decimal number 64.125, you need to convert this into its binary number, its equivalent binary number. Okay, so this is the second model. Now here it has two parts. One is the integral part and the second one is the fractional part. You need to treat both of them separately, okay, and write them in the with the same decimal representation with the same radix point. Now let us see how can we do this. Integral part is converted using successive division method. Fractional part is converted using successive multiplication method. Successive multiplication method. We have already seen what is meant by successive division method in the previous problem. So we will do it faster. So we need to divide that with 2. 64 must be divided with 2. Write the quotient separately, remainder separately, and do the division continuously until we reach 0 remainder. We got 0 remainder, right? Or until the division is not possible further. So 32. 2 times 32 is 64. Remainder is 0. 2 times 16 is 32. Remainder is 0. 2 times 8 is 16. Remainder is 0. 2 times 4 is 2 times 4 is 8. Remainder is 0. Next 2 times 2 is 4. Remainder is 0. And 2 times 1 is 2. Remainder is 0. And you cannot proceed further. And I need to move in reverse direction in order to write the equivalent binary for integral part. So 64 in decimal representation is same as 1 followed by how many zeros? 1, 2, 3, 4, 5, 6. So 1 followed by 6 zeros in binary. 1 followed by 6 zeros in binary. Next, coming to fractional part. So fractional part is 0.125. So you need to find its equivalent binary value using successive multiplication method. So first the given fraction must be multiplied with the base into which we need to convert. So the base into which we need to convert is 2. So I am multiplying with 2. Here if you observe, I am dividing continuously the number, the given decimal number with the base which we need to convert. Here I need to multiply the number continuously with the base into which we need to convert. So here 2 is the base. So I need to multiply this with 2. 0.125 into 2 is 0.25. 0.25, and you need to separate, or you need to write separately the integral value here. What is the integral value for this number? 0. So you need to write it separately and take this 0.25 once again, multiply with 2. So this is called as successive multiplication. Okay, as we are multiplying every time with the result again with base. What is 0.25 into 2? 0.25 into 2 is 0.5. Now for this, what is the integral part? 0. Decimal part is 0.5. So write 0.5 as it is. 0.5 into 2. What is 0.5 into 2? It is 1.0. So if you write 1 separately, you left with 0. When you have 0, you can do multiplication any number of times, you will get 0 value, because if you write 1 separately, you left with 0.0. What is 0.0 into 2? 0. You will get 0 value. If you do multiplication for n number of times, you will get the same value. So I want to stop here. Okay, so let me stop here. I'm erasing this. Here I need to stop. Now for the integral part, as I have moved in reverse direction, starting from last quotient to the first remainder, for fractional part I need to move in forward direction to write the equivalent binary value. Hence, the equivalent binary value for 0.125, which is in decimal representation, is nothing but 0.001. 0.001, right? Now, adding these two, you will get the equivalent binary value for 64.125. 64.125 with base 10 is same as 1 followed by 6 zeros in the integral part multiplied with the 001. Okay, you can verify your answer. Okay, how can we verify our answer? For the integral part, I think there is no need to verify again, because you have only one. Okay, one number of 1 in the integral part. So for this you will get 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6. 2 power 6 value is 64. So 64 into 1, 64. So you got the same value. For fractional part, I am doing verification of fractional part. Okay. What is the fractional part? 0.125. How can you do if it is 0.001? How can you do it? You, for this first 0, this is called as MSB and this is called as LSB. Moving from MSB to LSB, you need to multiply with the polynomials of 2 in a descending order. So for this 0, first 0, you need to multiply with 2 power minus 1 plus second 0 must be multiplied with 2 power minus 2 plus 1 must be multiplied with 2 power minus 3. So this value is 0, this value is 0, and you left with 1 by 2 cube. 1 by 2 cube is nothing but 1 by 8. So 1 by 8 value is 0.125. This is the same thing given in the problem. So the equivalent binary value for the decimal number 64.125 is 1 followed by 60.001. Okay. In this way, you can convert the given decimal number into its equivalent binary number, which has both integral part and fractional part. Okay. So for your better understanding, I just want to do one more problem. So two problems related to first model and two problems related to second model, right? So second type of problem is 16.675. This is the decimal number 16.675, and I need to convert this into binary number. How can I do it? You need to treat the integral part with the successive division method, and you need to convert the fractional part by using successive multiplication method. If you consider 16 as the integral part, so doing successive division, 2 times 8 0, 2 times 4 0, 2 times 2 0 remainder, 2 times 1 0 remainder. Hence for 16, what is the thing which you will get? 1 followed by how many zeros? 4 zeros. The equivalent binary value for 16 is 1 followed by 4 zeros. 1 followed by 4 zeros. So integral part complete. Next, for fractional part, you need to apply successive multiplication method. It is 0.675 into 2, because the base which we need to convert is into which we need to convert is 2. So you need to multiply with 2. What is 0.675 into 2? It is 1.35. 1.35. Now what is the integral part? 1. So write the integral part separately. Consider the fractional part again, which is 0.35. Multiply this with 2, right? So 0.35 into 2. What is 0.35 into 2? 0.7. 0.7. So write 0 because this is the integral part, and consider this decimal part again. 0.7 into 2. What is 0.7 into 2? 1.4. 1.4. So write the integral part separately. Consider 0.4 again. 0.4 into 2. What is 0.4 into 2? 0.8. Write integral part separately. Multiply 0.8 with 2 again. You will get 1.6. Write 1 separately. Write 0.6 into 2. It is 1.2. Write integral part separately, and you left with 0.2. Multiply with 2. 0.2 into 2, 0.4. Write 0 separately. So when you multiply with 0.4 again, you will get the same numbers repeated. Is it right or not? Here we have gone through 0.4 again already. So when you multiply the next number with the, means when you take the multiplication 0.4 into 2, you will get 0.8, and again 0.8 into 2, 1.6, 0. So you will get the same thing which is repeated. Okay, so we want to stop here because I want uh, because this multiplication is getting repeated and it is not ending anywhere, so I want to stop here, and I need this much accuracy. Means if you want to have more accuracy, you can consider more number of multiplications, but I want to stop here because this multiplication process is repeating again and again, so I want to stop here. And in order to write the equivalent binary value, you need to move in forward direction. Hence 0.675 decimal number is equivalent to 10, sorry, it is 0 point, right? So 0.10101010, and you will get like this because the same things are getting repeated, right? Now the equivalent binary number for 16.675 is nothing but 1 followed by 4 zeros multiplied with, sorry, point, radix point, 1 0 1 0 1 1 0. Okay, you will get the same thing repeated from here. 0 1 1 0. So 0 1 1 0, you will get the same thing. Okay, so when you convert the decimal number or the fractional part into a decimal number for your verification, you will reach a nearer value, not the exact value, because the multiplication is not converging. As this multiplication is not converging, when you want to go for verification, you will reach nearer value or an approximate value, but not the exact value. Okay, So do it for yourself, means up to this number, multiply with the polynomials of 2 in a descending order and check whether it is somewhat nearer to 0.675 or not. Okay. Anyway, it is easily considered as equivalent to 16. Okay, because it is 2 power 0, 2 power 1, 2 square, 2 cube and 2 power 4. 2 power 4 is 16, 16 into 1 is 16, so you will get the same value. But for the fractional part, we cannot guarantee that we will get exact value, because the multiplication is not converging. As the multiplication is not converging, you will get a nearer value. Okay, so 0.1010. Is it right or not? 1010110. How can you do it? Multiplying 1 with the 2 power minus 1 plus, for this 0 you will get 2 power minus 2. Next, for this 1 you will get 2 power minus 3. So 1 into 2 power minus 3 plus, I am considering only ones. 2 power minus 1, 2 power minus 2, 2 power minus 3, 2 power minus 4, 2 power minus 5 and 2 power minus 6. So 1 into 2 power minus 5 plus 1 into 2 power minus 6. Okay. So it is 1 by 2 plus 1 by 8 plus 1 by 32 plus 1 by 64. Is it right or not? What is this value? So please evaluate along with me. 1 by 2 plus 1 by 8 plus 1 by 32 plus 1 by 64. So you will get this value as 0.671875. So nearer, it is nearer to 0.675. Okay, because when you do further, means as these four digits are getting repeated, you can add still some number to this number. You will get some more nearer to 0.675. But I am stopping here because I just need this much amount of accuracy, right? In this way you can convert the decimal number into a binary number which has only integral part, or which has both integral part and fractional part. Okay, I want to stop here. In the next video we will understand decimal to octal conversion and decimal to hexadecimal conversion. I hope you like this video. If you really like this video and if you think it is useful for you, then please share and subscribe to my channel. Okay, bye everyone.